we propose a new method to detect keypoints from point clouds, the Keypoint Autoencoders. The presentation will be divided into 3 parts: a brief introduction of the problem and previous works, our proposal, and the experimental results of a method. Firstly, you may ask, what is a keypoint? Literally, keypoints are key points or important points in a point cloud. In most cases, these points are the points of semantics. In other words, these points have special meanings on the object represented by the point cloud. For example, this is a point cloud of an aeroplane. It makes natural sense that these points with semantics, which represent the nose, the tip of wings, the joints, and the tail, are a good set of key points. Points should be repeatable, that is, invariant under rotation or some noises on the point cloud, etc. The previous state-of-the-art, the USIP, makes intensive use of this property to get the key points. However, the key points extracted with USIP does not necessarily contain much semantic information, especially under low quantities of key points detected, which makes it less helpful for actual downstream tasks in that situation. Another work, ISNet, tries to find a subset of points that works good for specific downstream tasks. However, this also disqualifies it as a key point detector, as its output changes greatly with the downstream task. Our method mainly focuses on the nature that the points of semantics, contribute more information to the original point cloud than other points. This means that we should be able to reconstruct much of the point cloud from its key points. So here comes our framework of Keypoint Autoencoder, in short KAE, for keypoint detection. There are 4 major modules in our design: an encoder, a decoder, a proposal module to obtain key points from the encoder, and an optional auxiliary classifier. Suppose we want to obtain k key points. Then in the encoder, a point net is invoked to get k point-wise features. Then the features are transposed and softmax is applied to obtain the probability of each point to be the ith key point. The probability is passed on to the Keypoint Proposal module. We employ different proposal methods during training and evaluation. In the evaluation process, we select points with maximum post-softmax probabilities to be the key points. However, the process is not differentiable, so we employed a soft proposal method during training. Input points are weighted by the post-softmax probabilities, and a weighted average is calculated to obtain the key points. The decoder is composed of fully connected layers. The first block shares weights among points to get point-wise features. The features are reconstructed into a point cloud of same size as the input point cloud by the second block. Chamfer loss is applied between the reconstructed point cloud and the original one. In addition to the point cloud itself, meta-information such as the class of the object that yields the point cloud is usually available in the dataset, which may help improve the distinctiveness of selected key points. Thus, an optional point net classifier is branched from the key point feature layer and contributes gradient from the classification results to the network. Here are some examples of our detected key points in comparison to USIP. This is a bench. You can see that our method does not suffer from degeneracy and the low quantity of key points requested. Also, it is interesting that the ACKE method is able to detect automatically the symmetries shared among a whole class of objects, It abandons symmetric points, sparing more points for other semantics. A chair, a pot of plant, and that's the end. Thanks for listening.